In the early 1900s, many brilliant minds were changing the landscape of science. In particular, quantum theory was emerging and changing the way we viewed the atom. One of the great results of quantum mechanics was the orbital, which is where the electrons reside. An orbital should never be confused with an orbit. An orbit is a mathematically defined pathway. For example, how the Earth orbits the Sun. Using classical Newtonian physics, we can predict where the Earth will be on the orbit at some time t and where it was at some time t. In the past, you may have seen a similar simplified model of the atom where the electron is orbiting the nucleus on a mathematically defined pathway, which couldn't be further from the truth. An orbital is a much more complicated concept than an orbit. In fact, we know nothing about how the electron moves around the nucleus. Thus, quantum mechanics demonstrated that electrons did not move around in neat orbits, but existed in regions called orbitals with a fixed amount of energy. In simplest terms, an orbital is a three-dimensional region or shape, and you can expect to find an electron inside this shape 90% of the time. It may help to think of this shape as a boundary surface. The electron is more likely to be inside this boundary shape rather than outside the boundary. Let's apply this concept of boundary shape to the electron of the hydrogen atom, which has one proton in the nucleus and one electron in a surrounding orbital. If you imagine the electron as moving in a random manner with fixed energy around the nucleus, and then imagine that we take a picture of this electron every second for a day, a week, or month, we see that all these pictures laid on top of one another begin to form an electron cloud around the nucleus. Remember, all these hypothetical pictures or data points represent where the electron has been over time. If we now attempt to create a three-dimensional surface to encompass 90% of all these data points, we obtain a sphere, which is often called the boundary surface. The creation of this boundary surface for the hydrogen atom, which is called an s orbital, requires some pretty complex calculus. Thus, if an electron is in an orbital, the electron has a fixed amount of energy, and the orbital is a three-dimensional region around the nucleus that indicates the probable location of that electron 90% of the time. There are many different orbitals for the electrons to reside. The successive solutions or orbitals from quantum mechanics increase in relative energy. When we add the shapes to the energy terms, we get the following electron configuration diagram, which shows all the orbitals available for electrons to reside. The orbitals fall into one of four broad categories: s, p, d, and f orbitals. Interestingly, there is one solution each time an s orbital is obtained, three solutions of the same energy each time a p solution is obtained, five solutions of the same energy each time a d solution is obtained, and seven solutions of the same energy each time a f solution is obtained. In the next chapter, we will revisit this diagram in detail to aid in writing electron configurations. For now, let's just focus on what this diagram represents, the orbitals, and each of these lines abstractly represents an orbital. For example, the first line on the electron configuration diagram is the 1s orbital, and it is a sphere. This is where the first two electrons of an atom can be found 90% of the time. In addition, all of the s orbitals are shaped like spheres. The three 2p orbitals are shaped like dumbbells oriented along the three axes: the 2px, 2py, and 2pz. For convenience, your instructor will often shrink them down to a third of their size so that they are easier to draw. If we continue to go up in relative energy, the shapes of the orbitals become increasingly more complicated, as demonstrated by the 3D orbital shapes. And it is unlikely that your instructor will hold you accountable for these shapes. Although this diagram may look complicated, remember that each line abstractly represents an orbital, and that all of these orbitals overlap on the same atom. Here you can see that a 1s orbital is the first orbital that the electrons will reside in. Then the 2s orbital is on top of that. Then the 3 2p orbitals are on top of them, and so on, until the necessary amount of orbitals are present to house all of the electrons that an atom may possess. If orbitals are where electrons can be found 90% of the time, in the next chapter we will examine how many electrons are in each orbital and the order in which they are filled by an atom. The arrangement of electrons in an atom is known as the atom's electron configuration. Think of this as finding a home for each electron. Electrons want to be in the lowest energy arrangement called the ground state electron configuration, and to accomplish this we need to follow 3 basic rules. The Aufbau principle tells us the order the orbitals are filled. Aufbau is a German word meaning to build up. Just like building a house, we need to start at the bottom floor. When that is completely finished, we begin on the next floor. Thus, electrons are added to the lowest energy orbital first, and then we work our way up in relative energy. This means that on the electron configuration diagram, electrons are placed into the 1s orbital first, then the 2s, followed by the 2p, 3s, 3p, and so on until the necessary amount of orbitals are filled to house all of the electrons that an atom may possess. The next rule is called the Pauli exclusion principle, which simply translates to only 2 electrons per orbital with opposite spin. Within the electron configuration diagram, we will represent electrons as half arrows. The first arrow is up and the second arrow is down. Remember that each line on this diagram abstractly represents an orbital and that each arrow represents an electron in that orbital. Below the diagram is the electron configuration notation, which utilizes exponents to indicate the number of electrons within each orbital. The third and last rule is called Hund's rule, which states orbitals of equal energy are occupied by one electron before any orbital is occupied by a second electron. Now let's review these 3 basic rules. The first electron goes into lowest energy orbital, 1s orbital, which is the Aufbau rule. The second electron goes into that same orbital with opposite spin. The Pauli exclusion principle states we can only have 2 electrons per orbital, thus the third electron goes into the next highest energy orbital, the 2s. The fourth electron also goes into the 2s orbital, but with opposite spin, followed by the fifth electron filling one of the 2p orbitals. Hund's rule states that the sixth electron will go into a different 2p orbital because we should fill the orbitals one at a time across an energy level before pairing electrons. Subsequent electrons are added following these 3 basic rules until the required amount of electrons are added. To work this example problem, we first need to consult the periodic table to ascertain how many electrons are in a neutral atom of carbon. In the first chapter, we learned how to quickly deduce the number of electrons, and we will need this skill now. The atomic number of carbon is 6. Thus, a neutral atom of carbon has 6 electrons. Therefore, this problem simply translates to finding a home for 6 electrons. Following our 3 simple rules, we place all 6 electrons into our diagram as shown. Start at the bottom, working our way up, 2 electrons per orbital with opposite spin, and fill the orbitals one at a time across an energy level before pairing electrons. In this example, we have one more electron than the atomic number of fluorine. Thus, examining the periodic table, we see that fluorine's atomic number is 9, which means there are 9 protons and 10 electrons if we have a -1 charge. Thus, the problem is really asking us to find a home for 10 electrons. Again, following our 3 simple rules, we place all 10 electrons into our diagram as shown. In this example, the calcium atom has lost 2 electrons when compared to the number of protons. Thus, examining the periodic table, we see that calcium's atomic number is 20, which means there are 20 protons and 18 electrons if we have a positive 2 charge. Thus, the problem is really asking us to find a home for 18 electrons. Again, following our 3 simple rules, we place all 18 electrons into our diagram as shown. First, we need to consult the periodic table to ascertain how many electrons are in a neutral atom of gallium, which will be the same as the atomic number for gallium. Gallium's atomic number is 31, which means there are 31 electrons if gallium has no charge. Thus, the problem is really asking us to find a home for 31 electrons. Again, following our 3 simple rules, we place all 31 electrons into our diagram as shown. You are probably thinking that it is going to be very challenging to memorize and reproduce the electron configuration diagram template shown. However, if you have access to a periodic table, you can easily reproduce it. For example, if you simply read the periodic table from left to right, the correct order of orbital filling is obtained. 1s, 2s, 2p, 3s, 3p, 4s, then you go down a level for the 3D, back up to the 4P, 5S, down a level for the 4D, and so on. In addition, the periodic table tells us how many electrons go into each sublevel. For example, the S block is 2 elements across, thus 2 electrons can go into all the S sublevels. The P block is 6 elements across, thus 6 electrons can go in all the P sublevels. The D block is 10 elements across, thus 10 electrons can go in all the D sublevels. And finally, the F block is 14 elements across, which means 14 electrons can go in all the F sublevels. You may notice that when we compare the order of filling we obtained from the periodic table to the electron configuration diagram template, they are the same. Clearly, having access to a periodic table helps us reproduce the electron configuration diagram template. Thus, you should practice drawing this diagram on your own with the aid of a periodic table until you have mastered this skill. As you can tell, the keys to writing electron configurations are to quickly ascertain the number of electrons for an atom or ion from the periodic table, and to be able to quickly reproduce the template for the electron configuration diagram. Remember, you can use the periodic table to help you reproduce it. Then simply follow the 3 basic rules for electron configurations, and you should have no problems determining electron configurations.